Hello, welcome back to my channel. Today, let us learn the extracting metals in the middle of the reactivity series. So, some of the examples in this categories are zinc, iron, lead, copper. So, all of these belong to the moderately reactive metals. Okay, and they are usually present in the Earth's crust as sulfides or carbonates. And we should understand that whenever we have sulfides, it is very difficult to convert sulfides to their respective metal because they undergo decomposition. Okay, so they easily undergo decomposition, and hence it is always feasible to convert sulfides to their oxides. Similarly, carbonates also to their oxides. So we have the method called as roasting. So in roasting, there is the conversion of sulfide ore into their oxides, and then further reduction of the oxides to give rise to the pure metal. So now let's take an example, zinc sulfide. Okay, zinc sulfide is also called as zinc blende, and it is treated with oxygen, that is with by heating strongly in presence of excess of oxygen, and it is getting converted. So zinc sulfide gets converted to zinc oxide and sulfur dioxide. So this is an example of redox wherein zinc sulfide gets oxidized to zinc oxide and oxygen gets reduced to sulfur dioxide. So this is a redox reaction. Here we can understand, students, the method of or the definition of roasting. The sulfide ores are converted into oxides by heating strongly in presence of excess air. So here it's very clear that sulfide ores are getting converted to oxide because it is very easy to convert oxides to their respective metals by reduction. Now the second step would be reduction. So the metal or the element used for reduction is carbon. See, when we look at the reactivity series, we have zinc, which is less reactive compared to carbon, and hence reduction is more like a displacement reaction. Okay, so it is like whichever metal is more reactive gets displaced from its compound. So here also the same thing we can understand. Carbon is more reactive than zinc, so obviously zinc replaces carbon. Okay, I'm sorry, carbon replaces zinc, that is zinc is less reactive and hence it gets displaced by carbon. And this is again a reaction, that is redox. Zinc oxide getting reduced to zinc and carbon getting oxidized to carbon monoxide. And here carbon acts as a reducing agent. Okay, and on the other hand, zinc oxide is acting as an oxidizing agent. So reducing agent property we already know. It is a substance which will donate electrons and further it gets oxidized. So carbon is giving the electrons to zinc oxide and it is getting converted to carbon monoxide and it gets oxidized. Okay, and on the other hand, zinc oxide is oxidizing agent and it is grabbing electrons from carbon and it gets reduced to zinc. Okay, so this is about the um reaction of zinc or extracting zinc in the middle reactivity series. Now, when in place of sulfide, when we have carbonates, okay, now the method is going to be called as calcination. So let's go to the definition. The carbonate ores are changed into oxides by heating strongly in limited air. So for roasting, it was sulfide to oxide, and calcination is carbonate to oxide. So it's very simple. Just know this abbreviation C to C. First C is going to be first C stands for carbonate and the second C stands for calcination. So whenever you have carbonate ore, the method followed to convert them to their respective, to convert the carbonates to their respective oxides is going to be called as calcination. Okay, CC. Now, let's look at the reaction. Zinc carbonate. Zinc carbonate gets oxidized to zinc oxide and carbon dioxide. Okay, so now here it is clear that the amount of oxygen supplied to this mechanism is going to be very less, because already it is forming, it's already in the form of a carbonate. Okay, and hence limited supply of oxygen, but strong heating will give rise to zinc oxide and carbon dioxide. So now, carbon dioxide, since it is gaseous in nature, it will easily evaporate, and what is left out is zinc oxide, which is in the solid form. Now, further reduction of zinc oxide, similarly to the previous method, using carbon as a reducing agent, will we get zinc and carbon monoxide. Okay, so this is the method involved for extraction of moderately reactive metals, and in one such example, they have taken zinc. The next, there's one more method, okay, of reduction, that is by using metals like aluminium or sodium or potassium. So usually these metals, if you look at the reactivity series, let's go back to the reactivity series. So you can observe here, students, that potassium, sodium, aluminum, these are all the metals which are highly reactive. Okay, and when you want to reduce metals in the middle group, okay, that is zinc or iron or tin, lead. So for all these metals, or even manganese, for all these metals, we can definitely make use of um, reduction using more reactive elements like aluminium, potassium, and sodium. And here again, it is nothing but a very simple displacement reaction. Okay, if you observe aluminium and manganese, okay, so here it's clear that aluminum is more reactive than manganese. Hence, aluminum will replace manganese from manganese dioxide to give rise to aluminum oxide. Okay, and giving rise to pure manganese. So this way, reduction of metal oxides with aluminum also can be performed for extraction of the middle series, reactivity series. Okay, so let's go through the content. Aluminum is used as a reducing agent in extraction of metals from their oxides. For example, in case of manganese or chromium, they cannot be reduced by carbon. See, if you look at the reactivity series, what happens is carbon, okay, is less reactive than manganese. So hence you cannot use carbon to reduce manganese. So manganese, carbon can be used to reduce metals which are below its series. Okay, like iron or zinc or lead, or etc. But the metals which are above carbon cannot be, they are more reactive than carbon, and hence carbon cannot be used as a reducing agent. So hence we need metals like something very very reactive, which are in the top of the series, like aluminium, sodium, potassium, calcium, can be used to reduce oxides into their metals. Now, this is, as I already told you, it's a displacement reaction, because aluminium, sodium, potassium, calcium, if you see, they are more reactive than manganese, and they can easily displace manganese from its oxides. Okay. And what are the, and if you look at this example, it is again a redox reaction 2, wherein manganese dioxide is getting reduced and aluminium is getting oxidized. Okay, so manganese dioxide gets reduced to pure metal manganese, and aluminum gets oxidized to aluminum oxide. And it is also a highly exothermic reaction. So many times in exam, what happens is you can be expecting this type of question, wherein a reaction is given to you and they are asking you to identify the types of reaction involved in this particular equation. So this example, what I have displayed on the screen, manganese dioxide with aluminum, giving rise to manganese and aluminum oxide, is an example of three types of reaction. One is displacement, one is redox, and the and also it can also be an example for exothermic. Okay, so exothermic because lot and lot of heat is being liberated during this reaction. Okay, and hence there's one application which is called as the thermite reaction. So let's go through thermite reaction. The reduction of a metal oxide to form metal by using aluminum powder as a reducing agent is called as thermite reaction. So as I already told you, the energy which is being liberated, students, it is so intense, so huge amount of energy that it is usually used for welding purpose. Okay, that's called as thermite welding. So usually you can observe in the railway tracks or even in these heavy machines, what happens is a thermite process is being used, wherein this molten iron, okay, is being filled into the cracked metal pieces, so that it welds, or else it connects the two metal pieces together. Okay, so this way it's having application because of its a huge amount of liberation of energy. Okay, so joining the broken pieces of heavy iron objects like railway tracks or cracked machine parts. So let's look at the reaction. So we have iron oxide Fe2O3, and the oxidation status 3, okay, reacts with aluminum. So aluminum here is acting as a reducing agent, and aluminum is usually used in the form of powder. Okay, we are giving, it is giving rise to iron oxidation state 1 and aluminum oxide. So now this iron is in the molten form because so much of heat is liberated that iron totally melts and it is in molten form. And this molten iron is mainly used to weld the two metal pieces, whether it's about the railway tracks or whether it's about the machine parts or etc. Okay, so this is all about the video. Thank you so much. Please subscribe.